Okay, so are you guys ready?
As ready as I'll ever be.
Yes.
All right. Okay. So I was going to go really quickly over what the definition is for a Maclaurin series.
Yes. Sounds good.
Now, as I talked to you guys about last night, you know, there are many ways that you can create a series. That you can use a series you already know, and you can substitute in, or you can create a series using one you already know, and you can differentiate and get a new one, or you can integrate and get a new one.
We spent a lot of time practicing that today.
Yeah, and that really, you're going to be surprised at how much that's going to help you. And then there's another way, and that's by the definition of the Maclaurin series. I don't want to have to go through the proof of that. When I teach my students, I show them, you know, the proof of why that works. So if I just give you the definition, are you going to be okay with that?
Yes.
Okay. All right. So so we can say that a function f of x is equal to, if it's centered, because a Maclaurin series is a Taylor series, if it's centered at 0. I just think that they didn't have enough people to name things after, you know, so so they had to say that Maclaurin gets something too. And throughout history, I guess it's good to have things named after different people. But anyway, so a Maclaurin series is nothing more than a power series, and a power series is
There's an X in it.
there's a sequence of power functions, and power functions are like 1x, x squared, x cubed. So it's a series of adding all of those up, and then it's an infinite series, meaning that you have an infinitely many terms for this polynomial. But anyway, so to design one from scratch, they came up with this theorem for centered at 0, where it's f of 0 plus, and this is really over 0 factorial. And remember, I said 0 factorial by definition was 1. And you know, this is really times x to the 0 here, and x to the 0 is 1.
Mm-hmm.
And then f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial x cubed plus dot 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 plus, and then of course you can do the general, which would be the nth derivative. Oops, I was going to put x, but it's really 0. Evaluated at 0 over n factorial times x to the n plus dot dot dot. Okay, so that's how you would create one from scratch if you knew what the original function was that you were trying to find a power series for. Okay, so if you'd like to do one, we could do one for number 5, which is x e to the x.
Okay.
Is that all right with you guys?
Perfect.
Mm-hmm.
All right, so let's create a Taylor series then for f of x equaling x e to the x. And this is, I'm pretty methodical about how I do this. You'll notice in the definition of the Maclaurin series, you need f of 0, you need f prime of 0, f double prime, f triple prime. And so I do enough derivatives in order to see the pattern to come up with the nth term. Okay, so to take the first derivative of this, you have to use the product rule here. So it's going to be first, d second, plus second, d first. Of course, they're probably not used to the way I take derivatives, Mackenzie.
Yeah, with your little, like, way you say it.
Yeah, but anyway, I'm going to factor out an e to the x here because it's going to make it easier to take the second derivative. If that's all right.
Yep.
So we're going to take the second derivative, and that'll be the first one times the derivative of the second, which is 1, plus second, which is x plus 1 times the derivative of the first. And then I'm going to factor again an e to the x out. And then we get x plus 2. And then I'm going to take the third derivative, which is again using the product rule. I take the derivative of the first times the derivative of the second, which is 1, plus copy the second times the derivative, times the derivative of the first, which is e to the x. Did I do that right? Let's see. First. Oh, this is 2 here. Sorry.
Yeah. There you go.
First d second plus second d first. I get out of my rhythm there. And then this is x plus 3.
Mm-hmm.
All right, I'm going to do one more just to make sure we have enough for the pattern. And so it's the first times the derivative of the second plus second. I'm sorry, my allergies are killing me today here in Georgia.
I'll be back in Georgia in 2 days.
There you go. And this will be x plus 4. Well, so I'm seeing a pattern here because you notice the first derivative is plus 1, plus 2 is the second derivative, the third derivative is plus 3, and plus 4. So that's interesting. But we don't need f of x or all its derivatives. We need them evaluated at 0. So I'm going to go over here and evaluate them at 0. So when I evaluate it at 0 here, well, the first term is 0. And then f prime of 0 is, well, I'm going to go to this. E to the 0 is 1. Times 1 is just 1. So f double prime of 0 is equal to e to the 0 is 1 times 2, which is just 2.
Mm-hmm.
Triple prime would be 3. And the fourth derivative evaluated at 0 would be 4. And I could keep going here and say the nth derivative here, because I've seen the pattern, is e to the x times x plus n. Everybody see that pattern?
Yep.
And then over here, I can say that's just going to be n if we were to keep going. All right. So we can say that f of x, which is equal to x e to the x, can be approximated by, well, what happens now is I just take the f of 0 and plug it in here. But what happens? The first term doesn't exist because f of 0 is 0. Plus, now we're going to use this f prime of 0, and we get 1 over 1 factorial, which is just 1 times x. Plus, and then I'm going to take the second derivative evaluated at 0, and that's going to be 2 over 2 factorial. And I'm going to do this just so that we can kind of see what, the pattern is. Times x squared plus the third derivative is 3 over 3 factorial times x cubed. And since we have the fourth derivative, let's do that. That would be 4 over 4 factorial x to the fourth plus dot, 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 plus, and then I can use n over n factorial x to the n plus dot, dot, dot. And so I think I've got that right, but we could simplify this a little bit now. So what's happening here is this is going to be x plus 2, x squared plus 3 factorial is 3 times 2, right?
Yeah.
So I can cancel the 3 out. So this will be x cubed over 2 plus 4 over 4 factorial is going to be,
X to the 4.
it will be the 4's cancel, right? So that's going to be x to the 4th over 6 plus dot, dot, dot. Plus, now what happens here? The n factorial is really what in disguise? It's n times
N minus 1.
n minus 1 factorial, right? So we can cancel out the n's, and this is x to the n over n minus 1 factorial plus dot, dot, dot. So right here, I can put it in a summation formula and say the general formula is x to the n over n minus 1 factorial. Now we're going to see if this works. I'm going to let n equal something here to infinity. And I need n to be 1, don't I? First, because this has to have a 1 exponent.
Mm-hmm.
So I'm going to start at n equals 1. Let's see if that works. When I go n minus 1 factorial, that's 1 minus 1, which is 0. 0 factorial is 1. So that works for the first term. Let's see if it works for the second term. If I bump the counter up to 2, I get x squared over 2 minus 1 factorial, which is 1 factorial. So that works.
Mm-hmm.
Okay? So we just created the Maclaurin series for x e to the x by using the definition. So what is the process? You just take all of the derivatives and then you substitute 0 in for x to find out what all the values are so you can put them in the definition. All right, now,
Okay.
I wouldn't put my word for it necessarily because I am sometimes a doubting Thomas myself. So I'm going to suggest that we y equals x e to the x, and there's our function. And let's type in parts of our polynomial here, which are y equals, why on earth are we doing this, right? X
Plus, yeah.
Plus x to the third divided by, helps if I use a plus sign, doesn't it? Plus third divided by 2. You see how it's magically working?
Yeah.
It's so cool. This stuff to me is, it's like magic because, you know, these guys in the 1700s were able to, you know, figure out how to create these polynomials that fit functions so beautifully during an interval of convergence. Now, if you had to guess what the interval of convergence is here, just by looking at the sketch here, negative
Yeah.
1 to 1, doesn't that look like it would be?
Yeah.
Now, I don't know if I add more terms. We could add more terms here. Plus would be x to the, oops, if I use the caret, over 4 factorial.
4 factorial, which is,
Factorial. Good news is I can put 4 factorial.
oh, fantastic.
This is so wonderful. Anyway, okay, so it's looking like the interval of convergence is expanding. So I don't think it's negative 1. And how did we figure out what the interval of convergence is? Well, we'd have to use the ratio test. So it's kind of all fitting together.
Yeah.
And how, you know, we'd use the ratio test using this right here
Uh-huh.
to find what its interval of convergence would be all over, you know, if it's all real numbers or not, I don't know. I haven't, you know, obviously done this one. It looks like it might be because what is e to the x? E to the x is the sum from n equals 0 to infinity of x to the n over n factorial, and that converges for all real numbers. So I suspect this one might too, actually. So anyway, so that's the Maclaurin series. So the difference would be, and let's do not all functions do you want to know what the values are at x equals 0, right? It'd be nice maybe if we knew what the values were at, I don't know, x equals 1.
Mm-hmm.
So we can create a Taylor polynomial centered at 1 that be created centered at 1, and we can approximate that function centered at 1.
I'm sorry, are you talking about a Taylor polynomial or a Taylor series?
Well, okay, a series is an infinite polynomial.
Oh.
Okay.
Right, okay.
Okay, so yes.
Taylor series of this function instead of Maclaurin, right?
Right. And I am probably a little looser with my language than I should be, but a Taylor polynomial can have a finite set of terms, or a Taylor series has an infinite number of terms. But I like to think of a Taylor series as, because Taylor series sometimes can sound scary to high schoolers, especially. And when you say it's a polynomial, and the only difference between that and any polynomial that you've ever used in your life before you got to calculus is that it has infinitely many terms, you know? So I try to make it less scary by calling it that. So I apologize. So sometimes I slip in and out of that, but So a series, a Taylor series is an infinite number of polynomial terms. And a Taylor polynomial is a limited number where, let's say if I wanted the Taylor polynomial to approximate this function, I've got a Taylor polynomial here of degree 5 on the left, approximating x e to the x centered at x equals 0. So this is a polynomial, not a series. Well, it could be a series if I'm adding it up, but it's a finite series, not an infinite series. Does that make sense?
Yeah.
I'm rambling, I'm sorry.
Oh, no, yeah, I get it.
So shall we do this one centered at 1 so you can see the difference?
I have a question real quick. So,
Sure.
we were trying to do the ratio test of what we got. If you have, but then it gives you n minus 1 factorial on the right side of the top, and then you have n factorial on the bottom. How does that cancel out?
Okay, well, which one's bigger?
N factorial.
N factorial is bigger, so you deconstruct that one into n times n minus 1 factorial, and the n minus 1 factorials will cancel.
So you're just left with an.
Yeah, I'll do it. I'll do it with you. Because it kind of ties all the pieces together.
Yeah, yeah.
So, okay, so using the ratio test. I did suggest it. I should probably do it with you. That would be the nice thing to do. So we could say the limit then as n goes to infinity of absolute value of a sub n plus 1 over a sub n. Let's see, that would be the limit as n goes to infinity of, well, my term here is, let's get Desmos out of the way. My term here is this one here. So since this would give me a double-decker fraction, I'm going to flip it right away. So this would be x to the n plus 1 over n plus 1 minus 1, which would be, I'm going to show it because I am, OCD that way. I'm sorry. Over, and then I'm going to flip the second one already. So this would be n minus 1 factorial over x to the n. The limit as n goes to infinity of absolute value of. Now, this n, x to the n is going to go away with this x to the n, and left on top is just going to be the x. And this right here simplifies, as you stated, to n factorial because the ones cancel. And this one is bigger. Actually, this won't be, well, let's see. Let's see what happens.
I want it. I think it was.
This would be n times n minus 1. No, it's going to be all right, factorial. So this cancels with this, and we're left with x over
Just
n.
N.
And remember, when you take this limit as n goes to infinity, we don't care about the x. It's a constant because we're taking n to infinity, not x. Now, n is not really, x is not really a constant, but in this limit expression, it is. Okay? So what does this go to?
0.
0, which means converges for all real numbers. From negative infinity to infinity, its radius of convergence is?
Radius is.
All real numbers. Yeah.
Is infinity, yeah. So, so you don't have to check the endpoints here, which is really nice. But this will converge for all real numbers if you use infinitely many terms. Do you see how when I was expanding on the Desmos graph, the number of terms I used, the interval of convergence kept getting bigger?
Yeah.
That's why, because the more terms you use, the more accurate you're going to be. The closer it'll fit, the longer it will fit. It'll increase your interval of convergence. Okay? So let's do the same one, but let's have it centered at 1. Okay? Is that all right?
Yep.
That's a Taylor series now? Then?
That, yeah.
Yes.
We're switching.
Right. Yes, it's a Taylor series. Taylor, like I said, Maclaurin is a special case of the Taylor series centered at 0. I don't know why they just don't call them all Taylor, but I think Maclaurin needs credit too. So the good news is that we have all the derivatives already. Okay, because when it's centered someplace other than 0, the Taylor series, its definition, and this is going to be centered at x equals a. I'm going to call it a because most books use a. I don't know if your book uses a or c. It probably uses c, and then I put a. So that's going to be f of a all over 0 factorial plus f prime of a over 1 factorial times x minus a, which is the transformation from 0, plus f double prime of a over 2 factorial times x minus a quantity squared, plus, I'm going to go dot, 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 plus the nth derivative of evaluated at a over n factorial times x minus a to the n plus dot, dot, dot. Okay, so the only difference is instead of using f of 0, you use where you're centered inside your evaluation here. Okay, so what we need in order to create this one set, we're going to do the Taylor series. For x e to the x centered at, now I just chose x equals 1. Is that all right with you guys? We could do it somewhere else.
That's perfect.
That's fine.
I figure 1's a nice number. Centered at 1. Now, I'm going to go back to the sheet here because I already have all the derivatives. Because you do the same thing. You'd find all the derivatives, just like we did. And instead of evaluating it at 0 now, we're going to find f of 1.
Do they normally tell you how many terms they want you to find the derivative?
Well, you know, for the AP exam, they'll say, you know, state the first 4 non-zero terms and the general term. So they would want you to state like 1, 2, 3, 4 in the general. Okay? I don't know if your professor is going to say state the first 4 non-zero terms in the general, but to me, going at least 4 helps you with figuring out what the pattern is to find out what the nth term is. If that makes sense.
Yes.
Sometimes it takes me going to 5 or 6, but you get better at it the more of them you do. So, all right, so we're going to evaluate our derivative over here, our function at 1. So that's just 1 times e to the x, which is, or e to the first, which is e.
Yeah.
Really quick, can I also ask, what is the index for the Taylor series?
The index?
Yeah,
Index.
from what to infinity?
Well, for this one, I made it 1 to infinity. I mean, but we could, you know, the thing about summation notation is you can make it whatever you wanted. I mean, I could start this at 2, but then it would transform the way this looks. And I could start it at 0, and it would transform the way this looks in order to generate this power series. Does that make sense?
Yeah.
I could write an equivalent for this. And let's say I started at 0. Okay, if I start at 0 and go to infinity, I need my first term to have a power of 1. So this would be x to the n plus 1, because if I plug in n equals 0, I have to start at, you know, x to the first. Over, well, and then I need this to be 0 factorial on the bottom, so I can just say n factorial here. That would work. But they're equivalent. They look a little different, but they're equivalent. That makes sense?
Yeah. I just didn't know if there was one for the Taylor series standard or something.
Right, nope. Yeah, that just slows the grader down if you happen to have created your series that starts at a different location, which is no big deal. They should give you credit for either one of these answers. All right, so f prime of 1 is going to be e times, excuse me, 2. I'm telling you. Right, so that's just going to be 2e.
Mm-hmm.
All right, and then f double prime of 1. We plug in e to the first, so that would be e times, so 3e. This is a nice problem. I'm going to have to remember this one for when I teach this next year. Then 4e. No, wait. Yeah, that's, what?
Is it
Are the e's supposed to be to any exponent?
Oh, no, you're right. I'm sorry. No, they're to the first.
Yeah.
Because you're putting it one.
All of them are to the first?
Okay, because I'm
Oh,
plugging,
yeah. Okay.
you scared me for a minute because I thought, oh gosh, am I doing this wrong in public? I might be.
We're good.
Are you sure?
Yeah.
Okay. Because sometimes I get going and I, am looking
Yeah,
at
no,
the
no.
end.
Plugging in what I got in the parentheses. I don't even know what I was doing. Okay.
Yeah, but
we're
you're
good.
used to me. You get that. Okay, so the fourth derivative is going to be 5e. I'm starting to sense the pattern.
Mhm.
And then we put 1 in the nth derivative, and we're going to get ne, right?
Yeah.
All right, so now we're going to take what we know, the f of 1, f prime of 1 here. I'm going to try to get it all on the same screen. And we're going to compose our new Taylor series. So we're going to say f of x equals x e to the x, but we're going to center it at 1. So we're going to go f prime of 1, which is e over 0 factorial plus f prime of 1 over 1 factorial, which would be 1 e over 1 factorial times. Now, instead of x, we're going to have x minus 1 because you're centered at 1. You made a transformation. Plus, oh wait, this is 2 here. I'm sorry, because that's 2 here.
Yeah.
2e. All right, plus 3e over 2 factorial times x minus 1 to the second. Plus, now I'm going to use the third derivative, right? Because I've used the function, first derivative, second derivative, third derivative. Yep, you're right. 4e over 3 factorial times x minus 1 quantity cubed plus ... Now I'm going to go to the general because I've got the pattern. So it would be what? This one? Because we used, right?
Yeah.
We used
Yes. So it's
So it's n.
that
N-
over n fact. So ne
over.
over n factorial
Uh-huh.
times x minus 1 to the n.
Yeah. Plus ... Very nice. Now, so we can simplify this one a little bit, can't we? Because we know about n factorial and with an n.
Yes.
So I'm going to write this a little bit more simplified. This is going to be e plus 2e times x minus 1 plus 3e over 2 times x minus 1 quantity squared plus, I'm just going to leave the factorials in there. It'll be easier. 4e over 3 factorial times x minus 1 cubed plus ... Now let's simplify the general term though. This is going to be e over, I think I heard it, what?
Plus 1 factor. Just n plus 1.
N minus 1?
Minus
Minus
1.
Yeah, you're close. I like it. X minus 1 to the n plus ... And now we can write a summation notation. N equals, we need this first one to be to the 0, don't we? X to the 0.
Yeah.
But if I put a 0 in here, I get a -1, and there is no -1 factorial. So I'm going to have to start it at 1.
Okay.
And then we're going to go e over n minus 1 factorial, because then that would give us to the 0. X minus n, x minus 1 to the,
N.
yeah, no, it has to be n minus, hold on a minute, I got to check it out. I could do this right? Let's see. N over n factorial Oh, wait, should this be n plus 1 here?
That's what I had done the first time.
Oh.
Yes, I think you're right.
Yeah.
This has to be, this is n plus 1.
Times E, right?
Because
Yeah, I forgot the E.
yes.
Okay, so I was doing it right.
You were. It's okay to speak up because,
I thought there was something else. I did something else wrong too at the same time. I did two things wrong.
okay, so I'm going to write n plus 1 E. So I ran into it. Here, let me get my eraser. Because all calculus students should have a big eraser, even calculus teachers. Okay, so let me fix this one here too. Okay, so, oh gosh, and then this one would be,
N plus.
right, because this is 4 and this is 5, n plus 1 times E, yeah, duh. Goodness gracious, sakes alive. Okay. Plus dot, 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 plus. Okay, so I can't really reduce this, can I? Because the big one, which would be n plus 1, doesn't have a factorial, so we're stuck with it. All right, so let's write our summation notation. This should go a lot more smoothly now that we have that right. So now I can start at 0 and be happy. Because golly, starting at, yeah. The good news is when you try to find the nth term and set up the index of summation down here, it's really going to point out if you have any errors here. That's where I was like, wait a minute, you know? So that's going to set you up. So let's check a couple of terms here. When I plug in n equals 0, I get 0 factorial, and I get a 1 here, which I want. And then that would be e times x minus 1 to the 0, which I want. And then if I bump the counter up to 1, I get 1 factorial on the bottom. And then I get 2e to the x minus 1 to the first. So that's going to work. Okay? Now, do you believe that that will model our function at x equal 1, or do you want to see it?
I mean, I believe it, but
Okay, it's up to you. I
believe it. Okay.
So that's all Taylor and Maclaurin series are. You just take enough derivatives to help you see the pattern, and hopefully tomorrow you're going to have a function that's reasonable to take the derivatives of, and then you plug in, you know, the center to find out what the center's value is at these derivatives, and then you just plug it in the formula.
And what was your final answer here?
Oh, I'm sorry. Here, I'll show you. After I corrected that.
Plus 1 C times S. Yeah, that's what I got.
Gotcha. Okay.
And then the interval of convergence, you have to do the ratio test for that.
Yes, whenever you're doing the interval convergence for any of them, you should do the ratio test.
Okay.
Unless you have a geometric series. And yeah, for any of the Taylor or Maclaurin, you use the ratio test. And then you have to check the endpoints if you have a, you know, interval that is not infinite.
Yes.
Then could you give me kind of like an example of where it would be 1 point that's converging? Because I didn't find an example where that was the case. I know that it is, but I wasn't sure where.
Okay, that's going to be, let me get my book.
Oh, we did one.
We did, but that, I understand, because it looks weird, but it's really, what's really nice about that is that, hold on, let me get I like the Larson book because it has infinitely many examples.
Yeah.
That's alternating.
And then if you have any other like general questions, if you have other general questions,
Any like general questions that we have to give you after this?
Yeah, I was going to sorry, we should finish this session. Yeah.
That's the like approximation.
Applications of Taylor functions.
Yeah.
Let's see here, Maclaurin Series. Okay. All right. I'm sorry, hang on. That's the wrong one. I'm copying the one next to it. Okay. Okay, so this one is one that I think will fill what your question is. Okay. Now remember, for Taylor, for power series, because this is a power series, you have three possibilities. You can converge for all real numbers, you can converge over an interval, or you can then converge only at a point. So those are the only three possibilities. Okay, and so we're going to use the ratio test here. So that's going to be the limit as n goes to infinity of absolute value of a sub n plus 1 over a sub n. So let's do that. The limit as n goes to infinity of absolute value of, well, this is going to be 2 times n plus 1 factorial times x over 3 to the n plus 1 over 2n factorial times x over 3 to the n. So right away, I hope you see that the x over 3 to the n cancels with the n1 up here. And then we have to multiply this out. So this, the numerator out. So this would be the limit as n goes to infinity of the absolute value of 2n plus 2 factorial over 2n factorial times only x over 3, because it's now just to the first.
Right, 2n plus 2 and 2n plus 1.
Right, and now which one is the biggest?
The top is,
The top one. So that's the one that you would expand out to get to cancel things. So then you're going to get 2n plus 2 times 2n plus 1 times 2n factorial, because it had it embedded in there, all over 2n factorial times our x over 3. And so now the 2n factorials cancel, and we're left with the limit then as n goes to infinity of absolute value of 2n plus 2 times 2n plus 1 times x over 3. Oops, put my parentheses here. And now we're going to take n to infinity.
You get infinity.
That's right. So if I get infinity, remember with the ratio test, for it to converge, your limit has to be less than 1, which clearly is not the case here. It's greater than 1, so it diverges for all n. And there's only one possibility for this limit to be equal to something less than 1, and that's when x is 0.
Yes.
so it the 1 point that it converges for is 0.
Right.
In this case, you would just set the x over 3 equals 0.
At x over 3 equal to 0, so that's going to be at x equals 0. Because that's the only thing that's going to make this limit as n goes to infinity equal to something less than 1. So whatever this is, it could be x minus 3, it could be x minus 2, it could be x minus 1, it could be 2/3 x minus 79. Whatever makes that 0 is going to be it's the only point where it'll converge. that make sense?
Yeah.
So when you're doing these, like with the power series, and you get the limit after the ratio test to be infinity, that's when it converges at a point?
Yes.
Okay.
And it'll converge only when whatever's left,
The X thing, yeah.
whenever that is equal to 0.
Okay.
So,
Okay. Got it. Okay, so that's good for that section. So I think there's just one more section in the book that I sent you, which is like 11:11.
Actually, can we in 11:10 can we go over binomial series?
Oh yeah.
the what?
The binomial series.
Yeah, I'm not very good at that. I say I'm not very good at it.
Everyone here, so like I've asked like our professors and like one of the student tutors, like they say the same thing. They don't really have an explanation for it. If you don't, that's fine. There's kind of an explanation in the book, and I think we understand like what we need to do to manipulate it.
I think it's very formulaic. That's not in the the BC curriculum. So hang on, let me see here. That's what a binomial series is right here.
Yeah.
It's on, like, what, page 807? Yeah.
I mean, we have a formula for it.
It's got some weird combination thing going on. And
Right, what you're going to find really fascinating about this, and I haven't, it's like one of those things that I know about it, and if I see the formula, I can probably figure it out, but I've never had to stand in front of people and explain it, But what's really cool about the binomial series is that these are the coefficients for, like, let's say, it's to the third, right? If I say 1 plus x to the third, you see my book here, right?
Yeah.
Okay, so 1 plus x to the third. The only way that we've been able to expand that is use this thing called Pascal's triangle.
Yeah.
And the binomial series is what generates that. So look at, because with Pascal, remember it's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and it goes on, right? So if I have k is to the third, look at what happens. You get 1 plus 3x plus, this is 3 times. Remember, Mackenzie, when I said to you, when I was showing you this, when we would get 1, 4, 6, 4, 6, so 4, 1, and we were trying to figure out how we generated these numbers. And I said, that's really over our head. Well, it's because it's a binomial series, and that's how they do it.
Let me see. Okay.
So it's Pascal.
Okay.
It is so Pascal, which is really, really cool. So I just haven't delved into it enough to. So I guess what do you need to know is that if you have, this is 1 plus x to the 1/3, you write out what the binomial series is here,
Mm-hmm.
and then you plug in the number for k, and k is just the exponent. Do you see what I mean? So you might have to memorize this.
Yeah.
right. I guess my big question was like it's got that k choose n notation.
That what?
The k choose n notation.
I don't know what I don't understand what you're saying. Maybe I.
Like the combination of k choose n.
Oh,
Like
k choose n. Oh yes, I'm sorry. Yeah, now I got what you're saying.
What is really going on there? 'Cause I don't get what the significance of that is.
That's like n over like k times n minus k factorial. But I would memorize that. I would just memorize this.
Yeah, and then actually, could you flip back to that other page that you were just on for 1 second? The next one.
Yes.
Can you show us that chart of with all the That chart is better than ours. Is there any chance you could take a picture of that and send it to Mackenzie?
Yeah. Watch.
Ours doesn't include the intervals. It just says the radius. That's a lot.
I'm gonna hide this. You see this? I can hit a snapshot.
Oh, I like it.
No, technology is amazing. I'm never going to be a technology curmudgeon. All right, here we go. Compose.
That's what it starts.
No, that's not what I want. I don't want that. Do I? How do I took a snapshot. So where did it go?
Is it
Oh, I have a
going?
better idea. Hang on, give me a second.
You have to just send it to her, right?
She could, but then like the computer screen gets all. You know what I'm saying? Like, if you take a
Here, I'm
picture.
going to do it this way because I love my little snipping tool. That's
Oh,
Mackenzie.
you do like your snip tool.
I'm much better at that.
You love your snip tool.
I can do this. See, I'm much better at that.
Yeah.
Oop, I have to spell Mac Todd right.
See,
Have your
okay.
Gmail.
There it is.
Power Series. Oop. Send. Boom.
Perfect.
There, you should have it now. Okay. But yeah, I would just memorize the pattern here. Do you see the pattern? It's
Yeah.
1k, and that, and if it's if it's x squared, it's going to be two of them. So it'd be k minus 1. And then if it's x to the third, it would be k. There's going to be 3 of them. That's kind of how I would memorize it. Because if this is to the third, you're going to have k minus 1, k minus 2.
Yeah.
And then 1, 2, 3, 4 of them when you have a 4.
Okay.
Awesome. Thank you.
I just haven't ever, said anything about it out loud in public. But I'd be like you and just look at the pattern and hope that that's all I needed.
Okay, you
That's
guys.
more than a teacher told us about it, so thank you.
That is true.
Well, if I were going to require my students to know it, I would do a lot more research and tell you where it came from and all of that. But I just know that these are the Pascal numbers, like 1, 3, 3, or
Yeah.
1, 4, 6, so it's pretty cool. All right, well, so what I have to tell you guys is that if this is a 2-hour exam, they can't make it too incredibly difficult if half of it is your other stuff,
Yeah.
which is integration, right? And
It was, well, it's, is it, yeah, I know we have the format. It's 10 multiple choice questions and then 3 partial credits.
right, so how hard can they, if you know how to do this, I suspect, where you can generate your own Maclaurin series and your own Taylor series.
We're guessing that one of those, like either a Taylor or Maclaurin, would be one of the partial credits.
Right?
So like that would all be one question.
Yeah, that'd be one.
And then we're kind of just, we've been trying to speculate how they would put like if you were to make a question like a testing, like how would you put these series stuff in like a multiple choice question? Would they say like, what's the interval?
Give a power series and it'd be interval.
Okay. You guys are speaking my language. Here we go.
Are we going to Moodle again?
We are. You're not going to believe when I show you what you're going to see.
Oh goodness.
Those words make me happy.
Well, I'm going to log in as a guest, right? So you can see that you can log in as a guest. You just have to go to the website. That's moodle.btcatholic.org. You can log in as a guest, which is right at the bottom here. Log in as a guest. And you're going to go to mathematics, because you notice that I am still one of the old folks that uses Moodle because I think it's the best, but that's okay. We're going to go to my BC class this year. I'm clicking on it and it's okay. And then I'm going to scroll all the way to the bottom because series is the next to the last thing that I do. Okay, and it says it's under the infinite series topic. well, no, it's not. It's gonna be under my review. Looks like we made it. Do you see my review?
Oh, yes.
Okay, so you're gonna scroll all the way down to, let's see here. Right here, PC Calculus Review, multiple choice packet on series.
I
I-
see.
Okay, so I'm gonna click on that. I'm gonna click on it, it's gonna
Yeah.
pop up. Okay, here we go. And hopefully it's gonna pop up so we can see it. Here we go. These are the kind of questions you might see.
Okay. Okay.
And so there are, let's see how many are. There are 18 of them here on series. I'm going to minimize this. And then the answers I have are here for all of these tests for, of course,
Perfect.
it's small.
Okay, but yeah, we
So-
can all access that though.
So you can have series problems if you want. You can have differential equations. You can have applications of integration. You know, definite integrals, because that's probably what you guys would do. Applications, which would be volumes. I don't know if we're doing any volumes.
We
Area volume and surface area and
but that was all in our last test.
Oh, God.
The surface area ones.
I remember that
Yeah.
stuff.
but I have multiple choice for
All of that.
all of those.
Yeah.
Okay.
We're guessing
And,
though, keep it pretty straightforward on the stuff that's not series. Like we think the hard problems are gonna be series ones. Because we haven't had a test on that yet.
right, and the multiple choice on packet 7 here includes parametrics and polars. I don't know if you guys did parametrics and polars and
True. We didn't have to do the polar graphing. What-
Yeah, we did a little bit of polars. We didn't have to do like
It's
the
conic polar.
the conics we didn't do, but like regular polar we did.
Polar graphing, talk about that.
right. So this has some polar questions in here, but
Yeah.
you have, if you go to my Moodle site, you will have practice multiple choice questions for every calculus topic, and well, except for
Mom.
I don't know. Anyway, so, and then if you go to each one of like this is my parametric polar curve, you can look at my test, which has, I got a whole bunch of stuff. So
Okay.
on series, parametric, and polars, that might be of interest to you. Differential equations. I don't know if you did any of that with Euler's formula and proper integrals.
Yeah, we did have to do Euler's method. I remember that.
I've got a video on Euler's method here that you can
Yep.
link to.
Yep.
Logistic differential equations.
Oh yes.
Improper integrals, yeah, I got them all here, so.
Yep. Okay, but guys, we only have like one section left though.
And I'm going to go review these for the semester.
Yeah, but that's not.
Yeah, she said it's all true. You gotta memorize it.
Okay, so
The-
I think the
I
only
know
thing.
I would memorize.
Yeah, we have to learn the formulas. That's big. But yeah, I think the last thing that we need help on is like that section 1111 that I sent you a picture of. That's like the applications of like these Taylor polynomials. Like there's something about
Oh, actually, when you backtrack real quick,
to multiplying.
talk about the integral test and the remainder thing. Like backtrack.
Isn't
to,
that that's an approximation, right?
No, backtrack to the integral test, which is earlier in the chapter.
And what about the remainder?
What?
What about remainder?
Integral test. This was the integral test is like what 11.3.
Yes. So
The integral test, yes. So 11.3 is the integral test in the essence of sums. So we didn't really talk about that section with her. We kind of skipped over that.
yeah.
I just want to go through the entirety of 11.3.
Okay.
What's 11?
Does somebody
Integral
have?
test, estimates of sums, and then there's remainders in there too. And I don't think.
So we talked about the integral test.
Right, we didn't talk about the estimates of sums and the remainders.
Okay. So I think I'm gonna send you another picture then.
Yeah, so here, just
Okay.
take pictures of all 1.3. That's here.
me like the example.
Oh. Sure, that's like, right.
Okay, I just sent you another picture. This is like earlier in the chapter. And it's like estimating sums and something
Well,
about a
the title
remainder.
is the integral test and estimates of sums. So it's talking about that test. It's talking about estimating the sum of the series, and it's talking about something to do with remainders of the integral test. I have absolutely no idea what that means. Remainder estimate of the integral test. Yeah. So
Let's see what we got. Okay, so like on this question here that says explain why the integral test can't be used to determine, sorry. Like that?
well, so
Or
like that's
the-
because it's not continuous, decreasing or positive, right? But
Yeah, that's yeah.
Okay.
So to use the integral test, there are three conditions. The first condition is the function that you're going to take the integral of has to be positive. It also has to be continuous, and it also has to be decreasing. And so so cosine is going to alternate between plus or minus 1. For this one, the reason you can't use it for this one is that it's not always positive. It's alternating.
Okay. So then
Okay.
how do
I'm sorry.
you
So how do you do that one then?
well, you just figure something
you
out.
just
That's
do
an
a different
alternating series. You got to do the alternating series test.
I think we're all good on using the integral test, but I think what we never learned was about estimating sums of series and then the remainder estimate for the integral test. We don't really know what that is.
Remainder. I don't know what you mean by the remainder.
Oh,
I think the remainder like comes
Read what the book says.
later.
Which you got to give me a problem so I know more about what you speak.
Send her a picture of page like 763.
yeah.
I think I
Here, send a picture of this page.
okay, I'm sending you another picture.
Yes, ma'am.
763.
That's sums
Okay, so
remainder.
this is the little blurb that it says about estimating the sum. And that's about it. There's no information.
Yeah, the remainder was
Oh,
not
the
there.
remainder estimate. Yeah.
Right, that's right there.
So I just sent you like what the textbook says this is.
All right. Okay, so let's see. Oh gosh, did you guys ever do a problem with that?
I have
Let's see.
The teacher did not teach us this. He literally told us, like, I'm not gonna waste class time going over this, figure it out yourself. So,
Okay, well, hang on, let me read it. Suppose f of k equals a, where f is continuous positive decreasing function for x greater than or equal to n. Oh, okay. It's the proof. Okay, so this is the proof for the integral test.
Oh.
Okay, so let me explain what's going on. Okay, so for the integral test, it's like you can use oh my goodness, my voice. You can use a right Riemann sum, or you can use a left Riemann sum.
Gotcha.
And so it's like one of these is this one's the right one because it's, oops, sorry, I didn't mean to make it smaller, because that's n plus 1. And this is the left one because it's n. And so the remainder estimate is going to be in between those two.
right, would it ever ask us to estimate the sum of a series?
I've never, like this one says, approximate the sum of the series by using the sum of the first 10 terms. So let's see what this one.
That's like estimate the series only taking n to 10
Yes. Yes. Okay, so then you would just, you know, let's see here. Let me read what this says. I gotta change my unlock here so I can make it sideways so I can see the whole thing all at once. I'm a popular person tonight. Oh my goodness. Okay, so approximate the sum of the series of 1 over n cubed by using the sum of the first 10 terms. Estimate the error involved in this approximation. How many terms are required to ensure? Okay. So to estimate the sum, you would figure out what the sum is of the first 10. Okay, and then how do you estimate all the rest? Well, it's going to be I need the next page. I think it's going to be a sum. See, when we go from 1 to 10, we're going to do from, I bet you this will be 10 to infinity, right? Can you put a 10 down here? That's what I'm guessing. So can I see the next page? May I see the next page?
Yes.
That,
This thing?
and then, yeah, let's just look at the whole section. Yes.
But let me tell you, that's pretty darn nitpicky for trying to,
Oh, believe
see
me,
if-
our teacher is pretty darn nitpicky.
But
Right.
if he's not writing the test.
Right.
Okay. So I just sent you the rest.
I can see if you want to make multiple choice. I hope not.
Okay, so basically this whole estimation remainder thing is like the proof of it.
well, let me see. Let me see what the rest says here. Yes, it is.
Okay.
So I don't think personally. Now, if it's on there tomorrow, and I'm sitting here telling you you don't have to worry about it, I think that there are far more important things that you need to test over, which would be
Yeah.
all the other stuff. So I mean, because I don't want you to think about. I would focus on all the other stuff, and if this happens to be one of the 5 points you missed, that might be it.
Yeah.
Yeah.
Okay.
And I don't want to minimize that because you all probably want to get a 4.0 because I mean I understand that, but I think your time would be better spent doing something else.
Yeah, I think we're all just trying to do as well as we can. I think the problem with this teacher is like a lot of us, like we would need him to round us like a point. We can all get like 93s, but that's not an A. So
A 93 is not an A?
no, we have to get a 94 or above to get an A.
Oh wow.
Yeah. So
And there's no curve?
No. So I'm at like a 92. A lot of people in the class are like in the 90 to 92 range, and like we can't get it up that far.
We want to keep that in mind.
Yeah. So now our goal is to like keep the A minus at this point.
Oh, well, I suspect he might curve and you might not ever see it.
I
But,
hope.
But anyway, I'm not going to talk about professors because I don't know any. That's not something I know about. So
Yeah.
that's been many years. But the things I would focus on are the Maclaurin series, Taylor series, which I just did. I think that creating series from other series, like using substitution, knowing the chart that I just sent you, I would focus on, there's an application that's kind of a fun application. Like if I wanted to know or come up with a fraction for a decimal, and I'm just going to choose a random one, 4, 1 repeating, okay? If I wanted to come up with a fraction for this is really a series in disguise. This is an application of series. This is really 0.41 plus 0.0041 plus 0.000041, right? Plus, you see what's going on here?
Yeah.
So this would be 41 over 100, right? Plus 41 over I'm gonna put 10 squared here. Is that all right? That's easier for me to see.
Yeah.
And then 10 to the 4th
Mm-hmm.
plus 41 over 10 to the 6th plus dot, dot, dot. And then it'll be plus 41 over 10 to the 7th plus dot, dot, dot. I mean, to the n. I meant to the n, not to the 7th. My goodness gracious, what am I doing? Okay, do you agree
Yeah.
with that? And then you could say that this is actually a sum from n equals, oh, this would be to the 2n. From n equals 1 to infinity of 41 times 1 over 10 to the 2n, or just say 1 over n. 1 over 10 squared to the n. Could you do that?
How does that go to 41 over 99?
I'm sorry?
How does that 41 over 99?
I know, we're about to show you.
Okay.
Right? So this is, believe it or not, this is a geometric series. Geometric, meaning the sum from n equals 1 to infinity of a sub 1 r to the n minus 1, which is a blast from the past, maybe, yes?
Yep.
Oh yeah.
Well, if the absolute value of r is less than 1, this sums to a sub 1 over 1 minus r.
Oh.
Okay?
And okay, yeah.
Okay, and so what is r in this case? Well, it's 1 over 10 squared, isn't it?
Yep.
So what's a sub 1? Well, a sub 1 is that, right?
Yeah.
So this is going to equal
It's
41 over 100 over 1 minus, well, r is what here, 1 over 100?
1 over 100.
And we can find, this is going to be 99 over 100. So let's do 41 over 100 over 99 over 100, which is 41 over 99.
Yep.
This is a very famous application for series, and I put one of these on every one of my series tests because it ties together the geometric series idea and an infinite sum, summing up to a number.
Yeah.
And so this equals 41 over 99, but it's also an infinite series,
Yep.
which is really cool. And I just made this one up just now as we spoke. So
That's so cool. Okay. Okay. And then there's a little subsection I should have sent you. Like, how do you, it's like approximating functions by polynomials.
yeah,
How do you do that?
What section does it get to?
11.
Oh, okay. Well, that's not like it's the whole section, right? It's not a subsection.
Yeah, that's like
okay, so I'm going to go back to my Cosmos thing here real quick. And say I wanted to approximate, see, I'm centered here at 0, right?
yes.
So let's say I wanted to approximate right here, y of 1/2, because that's close to 0, right?
Mm-hmm.
Okay, this is y, or let's just call it f of x. Let's call it f of x. F of x equals 1/2. I'm sorry. Equals x e to the x, and I wanted f of 1/2. Well, that's just e to the 1/2 over 2, right? Because if I put 1/2, that's what it's equal to.
Yes.
But I don't have a calculator on me, right? I don't have a calculator. It's a real pain in the neck, but I don't have a calculator. But I happen to have a series over here. My hand will focus, please. I happen to have a series over here that will approximate it.
Mm-hmm.
Okay, so I can say f of 1/2 is approximately, I can use what they call a Taylor polynomial, which is going to be a limited string of terms from my infinite Taylor series. So I could use a second degree Taylor polynomial, and I'm just going to call it, I don't know if what your book calls it, but I'm going to go polynomial 4 of 1/2. I mean, second polynomial. This is the second degree Taylor polynomial.
Okay.
Okay, so there's my second degree. So my second degree, though, is only the first two terms of this. Do you see that?
Yeah.
So my second degree Taylor polynomial is x plus x squared. So let's see what happens when I do that. That's going to equal 1/2 plus 1/2 squared, which I can do without a calculator. This is 1/2 plus 1/4, which is 3/4.
Okay. So then in a question like that, would
Well,
it have to tell us which degree Taylor polynomial we use?
Yes.
Okay.
Yes. And so now I'm going to pull my handy dandy calculator out. I don't know if you can see it, but I'm going to type in this e to the square root of e, right? There's a second square root of diamond. E to the x, but I want it to be to the 1/2.
Mm-hmm.
Oh wait, e to the 1 because I have the square root there, divided by 2. And I'm going to go diamond approximate. Whoops, help if I have a parentheses. Around, I don't want it there, I want it here. And so what did I get as my approximation? This is 0.75, but my approximation using only the first two terms of my Taylor polynomial is 0.75. The actual is
0.8.
0.82. So that's not a bad approximation. What happens if I use
Third degree.
the third degree? Let's see what that looks like. If I use the third degree Taylor polynomial at 1/2, that's going to be 1/2 plus 1/2 squared plus 1/2 times 1/2 cubed, which is equal to 1/2 plus 1/4 plus that's 1/16. So I'm going to use my calculator. I know you're not going to be able to, but we could find a common denominator here. That's going to be what, 16. So that's going to be 8/16 plus 4/16 plus 1/16, which is 13/16. Is that right? I'm doing that fast. I'm adding in public, Mackenzie. Watch out.
I know.
All right. So now I'm going to see if 13/16 is closer to this 0.82. Is it?
Yeah.
Wow. Now I'm to the 100th. And how many terms did I use?
Just 3.
I just used 3. I didn't even use 4 or 5 or infinitely many. So if I were to use all 5, I bet you I would get to the even further play. It'd be 0.82, blah, 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 right?
Yeah.
You see, so that's how a Taylor polynomial, where you use limited numbers of terms of your infinite series to approximate your function value at a certain x that's close to your center. And if you're going to find the error, the exact error, you would say f of 1/2 minus your Taylor polynomial at 1/2. And you do the absolute value because you wanted to have just the magnitude of the error.
Okay.
Now this magnitude of this error, this is the exact error. Whoops, I can't spell error. This is the exact error. How can I spell exact? Goodness. That's the exact error. And you have several methods to approximate the actual error.
Yeah. Okay.
Which is, Lagrange error bound, alternating series error if you have an alternating series, but this is not alternating.
It's just the difference between your estimation and the exact thing.
Yes.
Got it.
Is. Yep. And they can't, if they're going to do this on a non-calculator section, they can't have any numbers that are really persnickety. They're really going to have to be nice.
Yeah, and they really don't like calculators, so we're probably definitely not going to get one.
But see, you could but see how easy this was to approximate
Mm-hmm.
it at 1/2? And you could approximate it at 1 even easier, so.
Okay. Does anyone else have any questions?
Once you talk about that, approximating, is that all that section is? Is that all?
Yeah.
Is that's not the whole section?
It is.
That's the whole section.
Literally, yeah.
Doing that?
Mhm.
Oh, that's easy. Okay.
Okay, so who else has questions?
Can we review power series? I'm good with that.
Review what? Power series?
Yes. Yeah, will you do one power series first?
It's like, yeah, just one more general like power series.
Like, okay. Well, okay, you'll have to help me with what you mean by that because Maclaurin series is power series.
Like the ones with the 3 cases where you find the
Oh,
right? Is that what you want? Or something else?
Give her a specific problem. What do you want her to do?
Should we choose you? No, that one's not. Like 1/4 plus x. Like, no, never. Oh, that's just a Maclaurin. Never mind. Okay.
okay, wait. Let me write down what you wrote. So f of x equals 1/4 plus x, right? That's, okay, so do they want it set, where do they want it centered?
They said x equals 0.
Oh, okay, so it's centered at x equals 0. Well, in order to do that, you got to factor out a 4, which is uncomfortable. So I'm going to factor out a 4 in the bottom. And what do we get? 1 minus x over 4. If I were to multiply that back in, do you see how that works? That matches this?
Yeah.
Okay. If for it to be centered at 0, remember, this is the one we know that's centered at 0, right?
Yep.
Well, what's wrong here?
Extra 4.
Do you see how I have a 4 here and not a 1?
Yep.
So I got to make that a 1 somehow. I used to call those problems, oh, I wish that was a 1.
So
To get this to match the series that we know, right, which is 1 plus x squared plus x cubed plus ... plus x to the n plus ... right? I got to get this 1 to be 1 here. So to do that, I factor out a 4, which is uncomfortable. But if you're factoring, if you go 2x minus 4 and you factor out a 2, what do you do to this 4 to get that 2? You divide, right?
Oh.
So that's all I'm doing here is dividing.
So then I times each thing by 1/4 and I plug in x over 4 where I see x.
Right. Okay, so what we're going to do is we're going to create a new series manipulating this one, and we're going to say 1/4 minus x is equal to 1/4 on the outside. I do it in 2 steps typically. And then where I see x, I'm going to put in, just like you said, x over 4 plus x over 4 squared. And I do it very, very methodically so that I try not to make a mistake, even though, I wish I was perfect, but that doesn't work out all the time. Ha, ha, ha. Here we go. So this is 1/4 times, well, what happens here? This is 1 plus x over 4 plus x squared over 4 squared. I'm going to leave it like this because it's going to help me with the pattern here. Plus x to the 3rd over 4 cubed plus ... plus x to the n over 4 to the n. And then I'm going to multiply 1/4 in. But what is that going to do to this exponent here?
Raise it by
Yeah, that's right. I heard it. I heard the silent one in the back say increases it by 1. But so it's going to be x over 4 squared plus x squared over 4 cubed plus x to the 3rd over 4 to the 4th plus ... plus x to the n over 4 to the n plus 1 plus ... So then I can write my series as n equals, now we're going to start at, this is a 1 here, sorry, at 0 because I need it to be x to the 0 here. Now I had the conversation, remember you could start it wherever you like, you just have to adjust your nth term to match Okay, and that's what your power series would be. And this is called creating a power series from one you already know.
All right, thank you.
Yeah, absolutely. And if I wanted to know the interval of convergence for this, remember, this is a fancy way of saying a sub 1 over 1 minus r. So what's r here? It's x
R.
over 4. So this is going to converge when x over 4 absolute value is less than 1. Or you could do the ratio test, and this is going to come out of the ratio test.
Okay,
All right, thank you. That makes so much sense.
got
It's
it.
really not bad once you get the hang of it.
Okay, does anyone else have any other?
I'm good. That was good.
Okay.
Thank you very much.
I think we're much more efficient this time than we were last night.
Well, you know, we were learning the technology bit too. So, hey, do me a favor and tell me what time your test is tomorrow.
It's at 11:15.
Well, I will say a prayer for you guys at 11:15.
Thank you.
Okay.
Thank you so much.
Thank